Human evolution from apes to modern beings has been a fascinating journey. Over time, humans stood upright, crafted tools, and eventually unlocked secrets of wheels. And similarly, modern humans progressed from writing on paper to using typewriters and eventually to personal computing devices.
Fast forward to today, the journey has not just stopped at personal computing devices. We have created something very extraordinary, a second brain. But this brain isn't about the flash and neurons. This brain is made up of circuits and algorithms, and we call it AI, artificial intelligence. This second brain now acts as a partner in our thought and has become a constant companion in attending to complex problems and daunting technical tasks. So, from helping us to analyze billions of data points to crafting strategies and even creating art masterpieces, it now acts as intelligence as a service and empowers individuals and organizations to scale their capabilities. So much like the wheel revolutionized how we navigate the physical world, this second brain revolutionizes how we navigate the intellectual world. We have not just created a tool, we have crafted a collaborator. The biggest example of such second brain are the path-breaking AI tools like ChatGPT, Gemini, and Llama, which have now become second nature, enhancing our creativity and productivity. But if we rewind the clock a few years back, AI wasn't quite as intuitive. Back then, the early neural networks like RNNs, recurrent neural networks, and LSTMs, long short-term memory networks, were the prominent network models to understand and process natural language. And these models helped automate tasks like text prediction, speech recognition, and even translation. Back then, it all seemed magical, but the magic had limits to use modern day parallel computing and supporting hardwares, limits to process large sequences of data, and limits to contextualize data. But when with the time, the requirements to process the complex data grew increasingly and exponentially, these models fell short. They couldn't stand. They were much like old ships trying to stay afloat in an increasingly complex sea of data.
Then came a revolution, transformers, with a very unique feature called attention mechanism. More on that later. These architectures were faster, sharper, and infinitely more context aware. But before diving into complex AI concepts, let's take a different approach. Instead of just throwing technical jargons at you, let's go through a story that will help you understand some of the biggest challenges faced by earlier AI models. Through this story, we will uncover how these models process information, why they struggle with long-term dependencies, and how context loss become a major hurdle. By the end, you will see why modern models needed something much smarter and paved the way for transformer-based LLMs with the unique attention mechanism. Okay, so let's start with the story. A thief has stolen valuable stuff from a king and has left him in a state of shock. Now king is unable to speak and tell exactly what has been stolen. You are a top detective of your time and have been summoned by the king's court to find out exactly what has been stolen. Luckily, this thief left behind a symbol as clue, and the clue is a half-eaten apple. To make sense of what does this half-eaten apple means, you flip through the pages of King's diary and look for references and connections. And every time you find something useful, something meaningful, you store it in your mental notebook as clues. And as you read King's diary page by page, sequence by sequence, you keep on piling your mental notes one by one. But here is where the things start to go wrong. The first problem that you face is your memory. Your memory fails you. Your mind processes information in a linear step-by-step manner. At first, it is easy. You discover clue 1, process the information associated with clue 1, and store the key details in your memory as your mental notes. Now, for the sake of brevity, let's call this processed information and stored mental keynote as P1. While at step 2 and processing clue 2, you combine previously processed and stored mental keynote, which is P1, with clue 2 information and produce next processed output P2. And in order to refine your thinking and make calculated guess, you have to keep on repeating this process with all the available clues in the sequence. But as a matter of fact, your memory is not unlimited, and this constant storing of step level information and aggregation demand high memory. While trying to keep track of clues as well as aggregated information, your memory starts to falter. And because of this memory constraint, while you try to remember current information, the information that you gathered and stored as mental notes from the earlier clues start to fade now. You vaguely recall reading about an apple earlier in the diary, but cannot quite decipher out that instead of just fruit, this half-eaten apple can also be a symbol or logo. And instead, your brain gets stuck thinking about a fruit, the apple. Let's give some name to this problem and call it vanishing gradient problem. In this problem, as you follow more clues, do more processing, and keep on piling your mental notes, the earlier clues fades, become less prominent in memory, and are very hard to recall when needed. The next problem you had was very slow processing. To make things worse, you can only read the diary one page at a time, in that too in a strict order. You cannot just jump back to an earlier page to double check something. It is like a conveyor belt. You process one item at a time. The next item cannot be picked up for processing until the earlier one in queue is processed, and so on. But if you quickly and suddenly realize you need to go back and rethink something, in this particular case, you are stuck. You cannot do that. So focusing on current clue and holding back all other information to be processed because of linear thinking puts a lot of pressure on your brain, resulting in a slow and inefficient processing. Let's call this problem a sequential bottleneck. In this problem, when reading text and processing words one by one in sequence, if something important is far back in the text, it gets harder to retrieve and slows everything down. And the third problem, and the most crucial one, was losing the bigger picture. The biggest challenge that you faced while solving this mystery is that your contextualization abilities were also severely limited in want of not having ability to jump back and forth between the clues. Understanding the stolen iPhone mystery required grasping subtle connections between the king's diary entries like words, king, apple, and iPhone had meaning that shifted depending on the context. At one point, apple is just a fruit. Elsewhere, it could mean Apple Incorporation, the brand. And the king might not refer to a person, but to a security system called the King's Vault. But because you're reading everything linearly, you treat every word the same way. You miss the hidden connections, and as a result, you lose the entire context of the story. Let's call this problem as context loss. In this problem, you could not grasp long-range dependencies, making it quite hard to understand nuanced meaning in a complex text. So, by the time you reached the last milestone, the connections between the clues and your mental notes grew weaker and weaker because information kept fading away as you traversed more into the sequence and reached the last step. Also, due to the issues with limited contextualization, you couldn't quite assemble the required pieces of puzzle and present the bigger picture. And finally, you presented a half-baked outcome which lacked story meaning, the proper context, and the required information to create the plausible solution. Now let's talk about the outcome. You presented a half-baked answer. When the king's court asked you to reveal the mystery, You confidently declared, "The thief must have stolen a basket of apples from your orchard." While technically plausible, your answer was completely wrong. It missed the deeper meaning. You would have solved this problem really well had your detective brain had these abilities to remember past information, process data faster, and understand context better. Also, your ability to focus on the most relevant words, jump between different parts of a text, and maintain a bigger picture understanding. In short, you lacked attention. Had you had a way to mobilize attention, you wouldn't just be reading the King's Diary page by page. You would be flipping back and forth, instantly recalling past clues and connecting the dots effortlessly and presenting the correct answer, which is the thief stole the king's iPhone and not a basket of apples. And this is what exactly happened with earlier neural networks or AI models, RNNs, recurrent neural networks, and long short term memory networks, LSTMs. While groundbreaking for their time, they struggled with tasks requiring long term memory and contextual understanding. They could solve small puzzles, could process small to medium sequences of texts, but were quite inefficient when piecing together complex stories or dealing with large sequence of text, just like you did with the King's Mystery. I hope this analogy was able to showcase the importance of attention mechanism in overcoming the challenges of earlier architectures like RNNs and LSTMs. Next, we will dive deeper into the inner workings of RNNs and LSTMs, breaking down gradients, backpropagation, and how RNN and LSTM units process sequential data. And from there, we will step up to the world of transformers and LLMs, exploring encoders, decoders, embeddings, and attention mechanisms, which are the very foundation of modern AI tools like GPT and Gemini. If you are eager to decode AI step by step, stay tuned, hit the bell icon for updates, and do not forget to like, share, and subscribe. Let's unravel AI one video at a time.